Hello, my teammates Mario Eugenia Galina and Alejandro Gonzalez and myself, Shuna Casone, will present our fifth delivery for our project titled Estimation of Obesity Levels Based on Eating Habits and Physical Conditions.
From the original dataset of 17 variables, we are only using 8 to test our hypothesis: gender, weight, height, frequent consumption of high caloric food, consumption of alcohol, time using electronics, physical activity per week, and level of obesity. In case more detail about the original variables is required, there is a link in the description of this video. It is worth mentioning that for our variable time using electronics, we are referring to the time where most of our attention is directed to the device and its content, keeping the person in a mostly sedentary state, such as video games, phones, TV, and others. The label level of obesity was determined by calculating the mass body index, which is defined as the weight divided by the square of the height. We decided to use these calculations as a continuous variable. The units for this variable are kilograms between square meters.
For our first scientific hypothesis, we propose that the demographic characteristics such as gender of a person can have an effect on their body mass index, or BMI. In order to test this, we propose the following statistical hypothesis. As null hypothesis, we propose that the average BMI in males is smaller or equal than the BMI in females. As alternative hypothesis, the average BMI of females is smaller than the BMI in male subjects. BMI is a continuous variable with units of kilogram over meter square, and gender is a categorical variable, either female or male. In previous deliveries, we have already determined that BMI follows a log-normal distribution. As it is shown, the R-risk distribution package in R gave us the best fits for our data, which then was tested by 1,000 bootstrap simulations and goodness of it, and we can see that the BMI does follow a log-normal distribution. For the log-normal distribution, we calculated the following parameters. In equations 1 and 2, we can see the formulation to get the expected value of our data and the standard deviation. Equation 3 shows the PDF of the log-normal distribution, and in equation 4, we can see the log likelihood function. The log-normal distribution has two parameters, mu and sigma. In order to get these parameters, we calculated the MLE by using the first derivative of the log likelihood function. The MLE for each parameter are shown in equation 5 and 6. In equations 7 and 8, we can see the information functions for each parameter. These were calculated by using the second derivative with respect to each parameter of the log likelihood function. In equation 9 and 10, we show how to calculate the variance of these parameters just by getting the inverse of the information function. In this slide, we show the value of mu and sigma obtained from previously mentioned equations, as well as their variance. We can appreciate that the variance of sigma is smaller than the variance of mu. Because of this, we will consider sigma as a known parameter. By using equation 1, we can calculate the expected value of x, and using the delta method, we can then calculate the CRLB, Cramer-Royal lower bound. This process is shown in equations 11 and 12. We then perform 1,000 bootstrap simulations from the original data, and we can see that the bias of 76.6% of simulations is lower than the CRLB previously calculated. Our grouping variable is gender. This variable follows a binomial distribution as it only has two possible values, either male or female. In this slide, we can briefly see how this grouping variable is distributed. To test our first statistical hypothesis, we divided our data into groups, either male or female. Then, for each group, we calculated the MLE for mu and sigma, as well as the information functions and variance. We then calculated the expected values for each group and variance by following the delta method previously explained. On the right, we can see the plot of the distribution of both groups. There is some overlapping between these two plots. Because of that, we cannot reject our null hypothesis. In this slide, we present the process to obtain the exponential family canonical form of the log-normal distribution. Equation 11 shows the format of the exponential family. In equation 12, we can see the canonical form. Equation 13 shows the canonical form of the log-normal distribution. From these, we can conclude that the log-normal distribution belongs to the exponential family, and as such, a conjugate prior distribution can be obtained in order to perform Bayesian analysis. The conjugate prior for log-normal distribution with known variance is a normal distribution. We previously calculated the variance or sigma squared of the BMI variable of the whole dataset. We will later use this value to calculate the posterior hyperparameters. We started by performing 1000 bootstrap simulations on each group of data. For each of these simulations, we then calculated the value of mu. We ended with a dataset with 1000 mu's for female and 1000 mu's for male. We then fitted these mu's in a normal distribution and calculated the following mu and sigma squared. These are our prior hyperparameters. With these hyperparameters, we then plotted our prior distribution, which can be seen on the right side of the slide. For the posterior distribution, we know that the posterior follows a normal distribution. In order to calculate the posterior hyperparameters, we use equations 19 and 20. Following that, we can see the values obtained for mu and sigma squared for both female and male. And on the right side, we can see the plots of these posterior distributions. We can see that there is a very small overlap between these two plots, and because of that, we cannot reject the null hypothesis. In the case for this statistical hypothesis, we can see that both the Fisherian and the Bayesian approach deal the same results, both reject the null hypothesis.
Our second scientific hypothesis states the excessive use of electronic devices and lack of physical activity can be associated as a factor to increase the BMI of people. To test this hypothesis, we formulated the following statistical hypothesis. Our first null hypothesis goes: subjects that spend excessive time using electronics have a larger or equal average body mass index than subjects that spend less time using electronics. And our alternative hypothesis states, subjects that spend excessive time using electronics have a smaller average body mass index than subjects that spend less time using electronics. For this hypothesis, we are considering excessive use of electronics as higher than 5 hours per day. And our second null hypothesis is subjects that do not perform any physical activity have a larger or equal body mass index average than subjects that make some physical activity. And its alternative hypothesis is subjects that do not perform any physical activity have a smaller body mass index average than subjects that make some physical activity. The variables involved in this hypothesis are the BMI, which is continuous, the time used in electronics, and the physical activity, which are categorical. Our variable time using electronics has three possible outcomes, which can be considered each as an independent event. Therefore, this variable should follow a multinomial distribution. However, our hypothesis groups this data into two groups: those who use 5 or less hours electronics per day and those who use it more. Therefore, this variable should follow a binomial distribution. With our data divided in two groups, 5 or less hours and more than 5 hours, we calculated for each group the MLE for mu and sigma, the Fisher information, and also the variance. Then, we calculated the expected value for each group and the variance with the delta method. We can see the plot of this information, and we can see that there is overlapping between the two curves. Therefore, based on this, we cannot reject our null hypothesis. Here we demonstrate that the binomial distribution belongs to the exponential family. Equation 18 is the format of the exponential family, equation 12 is the canonical form, and the 19 is the canonical form of the binomial distribution. So we can apply a Bayesian approach. The conjugate prior distribution for log-normal distribution is a normal distribution with known variance. We perform 1000 bootstrap simulation for each group, equal or less than 5 or more than 5, and then calculated the value of mu for each group. We obtained 1000 mu's after this process and fit this data in a normal distribution, and then calculated our prior hyperparameters. We can see our prior distribution plotted in the right side of this slide. To calculate our posterior distribution, we compute our calculations using equations 19 and 20, and our previously found mu and sigma. Then, we plotted this information and we can still see overlapping of the curves. So, our null hypothesis is still not rejected. The variable of our third statistical hypothesis is physical activity per week, and just like before, has several outcomes and should follow a multinomial distribution. However, to group BMI data according to our hypothesis, we get two groups from this, no physical activity and some physical activity. Then we establish that this variable follows a binomial distribution. Just like before, we calculated for each group the MLE for mu and sigma, the Fisher information, and the variance. Then we calculated the expected value for each group and the variance with the delta method. We then plotted this information and we got an overlapping. And based on this, we do not reject the null hypothesis. To get our conjugate prior distribution, we again have log normal distribution and we know that this is normal distribution with known variance. Then we again run a simulation 1000 times to obtain 1000 mu's, and after this process we fed this data in a normal distribution and then calculated our prior hyperparameters. We plotted this information and we still can see a little bit of overlapping. We plotted this information and we still can see a little bit of overlapping of the curves. For our posterior distribution, we input the values that we previously obtained, again in the following equations, and then we plotted the results. And we can see that although there is no more overlapping, the curve corresponding to no physical activity is more to the right, so it has a greater value as stated in our null hypothesis, so it is still not rejected.
Our third scientific hypothesis states that eating habits are strongly related to the level of obesity of a person. And we propose two statistical hypotheses. For the first one, the null hypothesis is that the proportion of subjects that frequently eat high-caloric foods with any type of obesity is larger or equal than the proportion of subjects that frequently eat high-caloric foods without any type of obesity. The alternative hypothesis is that the proportion of subjects with any type of obesity that frequently eat high-caloric foods is smaller than the proportion of subjects with any type of obesity that do not frequently eat high-caloric foods. The second null hypothesis states that the proportion of subjects with obesity that consume alcohol is larger or equal than the proportion of subjects without obesity that consume alcohol. And its alternative hypothesis is that the proportion of subjects with obesity that consume alcohol is smaller than the proportion of subjects without obesity that consume alcohol. The variables involved in this hypothesis are the level of obesity, which is categorical, the FABC, which is categorical yes or no, and the CALC, which is categorical, including no, sometimes, frequently, and always. Because the FABC variable, frequent consumption of high-caloric foods, has two possible outcomes, yes or no, we consider each subject an independent event, and the variable follows a binomial distribution as we can see in the image. We then proceed to perform the maximum likelihood estimation and the Cramer-Rao lower bound for FABC. We perform a simulation of 1,000 resamples, replacing the original data, and then each sample has 498 observations. From this, we get that the estimated proportion is 0.69 and the variance is 4.22 10 minus 4. So by using the variance as a threshold, we can see that 706 samples are below the line, meaning that more than 70% of the information is below the line. Now, separating the proportions of FABC into obesity and not obesity, we can plot using a normal distribution where we can see that the proportion of obesity is 0.67 and the proportion of not obesity is 0.71. Now, if we look at the plot, we can understand that the proportion of not obesity is larger than the proportion of obesity. Thus, the null hypothesis can be rejected. In this slide, we can see the equations that prove that the binomial distribution is part of the exponential family. Because the binomial distribution is part of the exponential family, we can then perform the conjugate prior. Now, for a binomial distribution, we need to fit a beta distribution. So we did 1,000 resamples of separated data with obesity and not obesity, and then calculated the p-parameter for each resampling, obtaining two datasets of 1,000 parameters. Then, these datasets were fitted to a beta distribution, obtaining the alpha and beta of obesity and the alpha and beta of not obesity. After performing the conjugate prior, we can then obtain the posterior distribution. As we know that the posterior follows a beta distribution, we can calculate using the equations 22 and 23 the alpha prime and beta prime of obesity and of not obesity. Plotting the results, as we can see on the right, we cannot conclude the same as with the Fish-Sharing approach with this Bayesian approach, because the null hypothesis cannot be rejected based on the plot. This is because, as we can see, there is an intersection of the plots, there is an overlap, so this means that the proportions can be equal, which does not let us reject the null hypothesis. Now we proceed to see the distribution of the CALC variable, CALC, frequent consumption of alcohol. Now this variable has four possible outcomes: no alcohol consumption, sometimes, frequent, and always. And we can consider this follows a multinomial distribution. However, we can also consider the CALC variable as having two possible outcomes. Therefore, we can now consider that this variable follows a binomial distribution and is part of the exponential family. Performing the maximum likelihood estimation and the CRLB, similarly as with the FABC variable, we obtain an estimated proportion of 0.64 and a variance of 4.62 10 - 4. And plotting the variance as a threshold, we can see that 707 of the 1,000 resamples is below the line. Thus, more than 70% is below the line and the result is correct. Then, separating the proportions into obesity and not obesity and fitting them into normal distributions, we can see the result of the right. In this plot, we can see that the proportion with obesity is larger than the proportion with not obesity. Thus, we do not reject the null hypothesis. Once again, because the binomial distribution is part of the exponential family, we can perform the conjugate prior, and its distribution is going to be a beta distribution. After performing the 1,000 resamples for each parameter obesity and not obesity, we can compute the alpha and beta for obesity and for not obesity of the conjugate prior. Here, we compute the alpha prime and beta prime for the beta distribution of the posterior, for both obesity and not obesity, and we plot them on the right. In this case, we get the same conclusion with the Bayesian approach as we did with the Fish-Sharing approach, as we do not reject the null hypothesis. This is because the proportion of obesity and not obesity can be equal, as it is noted in the overlap of both beta distributions. So now the conclusion is the same of not rejecting the null hypothesis, even though the plots look significantly different, in contrast to the case of the FABC variable.